Hey everybody, this is Dark Guardsman, and we're back, and we're going to do a little bit more visualization. I know you guys are probably getting tired of hearing about mathematics and seeing software that is not Minecraft, but I kind of like to show this stuff off as it does give me an opportunity to kind of show things that you can do that are Minecraft related that aren't necessarily just Minecraft based, but still influence it. So since last time, I went through and I actually worked on the application some more. It is now part of its own repository on GitHub, so if anybody wants to contribute towards it, they can pretty much go and find my private GitHub account, because I didn't put this up on the organization account just in order to actually make things easier to manage, because this is not related to the mods but kind of is. So if you actually go in and you dig down into my thing, you'll find a thing called the ICBM mod calculator. What I'm going to do is I'm going to make a calculator per mod, and I'm going to keep it separated. That way you guys can download these, and you don't have to download a huge file to get a thousand or so calculators that you may not want to use. Because what we're going to end up doing is we're going to put a whole bunch of different tabs in here. Each tab is going to end up doing a different thing. Now, as you can tell, the next part I was actually going to say is that I actually did add tabs. So the first tab is going to do the path stuff, so if you do the calculating in here, you can actually do things. I actually have fixed several bugs in this. There was some scaling problems. I added a border here so you can more easily see things. Eventually what I'm going to end up doing is actually adding a ruler to the bottom of this so you can actually see what the distances are and more easily understand this with the information that's going on. Same thing with inaccuracy, it's the same plot thing. Actually, both of these use a reusable object called a plot panel that I actually have written, and it's written in AWT, and it's built into a swing component, so that this panel can be used for anything, so we'll probably end up using this for other stuff. But with the inaccuracy, this is basically calculating what the inaccuracy pattern will look like for your missile when it impacts. You can use this to predict the likelihood of you hitting a target or not. So say you were going with the default 30 inaccuracy, which is what you get when you don't put any support frames on your launcher, is it's 30 by default. And say we're going to fire 1,000 missiles, and we want to see, okay, what does that 1,000 missiles look like? Now this isn't a good example because the color is really bad, and I'm actually planning on actually fixing that here later today. But here we can see purple dots, so we can see, yeah, it's pretty close to the cluster middle here. And we can mess with the inaccuracy. Say we go, as a modpack developer, I want to change the configs, and I want to set the minimum inaccuracy to 10. Or the default inaccuracy to 10, because it is modified per launcher, so you actually can set the launcher inaccuracy separate from the base with no frames on it. So it's clear the display and run this again. So you can see that's what 10 looks like. Now, the reason why it's in an oval shape is because the width and height are not proper, so if you actually move this up, you'll see it spreads out a little better. I will end up fixing this so that way it looks like a circle. It's very easy to do. All I have to do is force the plot panel to have an X and a Y that are even with each other in order to get things. And by the way, you can set the plot panel to whatever you want. So this one, unlike the other one, the plot panel is not optional. The reason this is not optional is what it does is it picks a point right in the center of the plot, and it needs these two values to be set. So if you set these to something really low or stupid, you're actually going to get some really crappy values. So if you did something like this, one, you're not going to see anything because most of your inaccuracy is going to be off the scale, and the page is not going to render properly because it's somewhere probably in the middle here. Like, or actually, you know what? I hit the clear display button again. I'm going to probably get rid of that button. As you can tell from a usability point of view, it's not really helping. But see, yeah, if you did a 10 by 1,000, it would mess the data up. Cool thing about this, though, if you guys want to make any kind of artistic system, you can sit here and just play with the calculation and get some really cool values. I've been playing with it all day, doing really interesting stuff, making some kind of little dioramas going on here, doing all kinds of really fun things. Let's do something like that. And you can actually sit here and play with this, and you can check all kinds of inaccuracy patterns. You can figure out what exactly is going on. And what I'm going to eventually end up doing with this is the reason why I actually made the inaccuracy. So I didn't just make the inaccuracy so we had another visualization tool, although that would have been just as valid as an excuse. I'm going to play around with the math. Right now, when it comes to the actual math for the inaccuracy, it's really simple. And it's better than the old 1.6.4 version. So some of the people will point out, well, the new version doesn't work like the old version. The old version just kind of randomized a target position. So what you ended up getting was something that sort of worked but didn't quite work. And what it would inevitably end up doing, and if I pull out, say, something like paint here to kind of explain this more better. So the new one does something like this. You get an accuracy pattern like this, and everything would end up that. Like the old version would end up like that's not exactly the shape I want to work on. So say we were launching our missile from down here in the corner. This would guarantee that your inaccuracy pattern is always a circle. The old one, what would end up inevitably happening is your inaccuracy pattern would look like this, kind of. It didn't quite work properly, and this shape would be the same no matter what direction you fire it in. The plan that I want to get to is end up with an inaccuracy pattern that looks something like this eventually, so that way your inaccuracy pattern matches what would be expected from an artillery shell. So an artillery shell in real life, the reason why it ends up with an accuracy like this is that the wind can push it left or right. So push it left or right, and then due to other forces like drag and stuff, you can be pushed back, or say you don't have a lot of drag, you can be pushed forward or something like that. So there's a lot of factors that come into play, but those are the two main ones, is drag and wind, and they push the round around. The ideal is the missile would have the same problem, is it would be pushed slightly off course due to the fact that there's a slight inaccuracy. The old code pretty much randomized it. You would almost always have, I think there's a video up here somewhere on my channel that actually shows this, where I was working on fixing this code, where the inaccuracy it sucked. You almost always could predict where that missile was going to hit 100% of the time, simply because the inaccuracy pattern was not actually an inaccuracy pattern. How it really worked is it would randomize, it would get a random value, then it would actually, it wouldn't get just one. It would get 4 random values, was the one that I eventually replaced. The one before that was 2 random values. So what it would end up doing is it would plus the random values to the X and Z, and you would end up with almost always having, say, if we were firing our missile from here to there, you would almost always end up with all of your inaccuracy missiles over here on this side. You would almost never get anything over here, and you would never get everything over there. So what ended up happening is our inaccuracy pretty much looked something like this instead of looking like a circle. So you would get nothing on the other side of it, and you would almost nothing in the middle here, and you would get almost nothing up in the north here. So you'd almost always had this, and plus you would never have anything behind the missile. So if your target was exactly that line right there, you would almost always get stuff in the corner, was what the old pattern went to. Then I kind of fixed it over time, made it so that way you would also get inaccuracy over here. And then I was like, you know what, that's not any good either, because we're not getting decent inaccuracy. So now we have a circle. And how this pattern works is, one, we randomize the inaccuracy to start with. Then we figure out a random rotation value. So we go, okay, if we're going to have this inaccuracy range, we're then going to have an inaccuracy of around the circle by a certain degree amount. Then we figure out some kind of vector from that. Then we times that by the actual inaccuracy pattern, and that gives us pretty much a line. And how the way to visualize this for those who didn't quite understand it, let's see if we can Control A and delete this whole thing, is that if our original impact point would have been here, what we're doing is we're selecting a random distance, then we're selecting a random rotation, and we'll end up like right over there. And each time a new missile falls, it does the same exact thing. We're going to figure out a random distance, say we are random distances like here, and then we're like, hey, we're going to land this degree. And then we do the next one, and it would come in and say, okay, this is our random distance. And then we're going to figure out a random degree, and we end up down there. So we end up with a much better, much smoother, and actually more truly random impact crater. Which ends up really, really well. And that's what this calculator actually simulates if we set this back to 1,000 and actually hit calculate again. Display doesn't work perfectly. Yeah, you can see, by the way, when you set this, it will set the coordinate there. But yeah, we end up with a much better display of the information. In a much more random thing. The display shows us what's going on and visualizing it. And what I'm going to end up doing is coming back in here later and toying with it, as I said, and what we'll see is a whole bunch of different values over here. And then once I figured an algorithm that looks right and it kind of gives me what I want, then we'll import it into the game like we did with the last algorithm. We'll keep doing this with all this stuff as well. So more likely I'm going to play around with something for the EMP tower, although to be honest, for the EMP tower it doesn't matter as much. Although we do use in the 1.7 version a different algorithm than we do in the 1.12. The 1.7 version of Voltage, which has an EMP built into it, actually does do a ray trace system, and I may end up implementing that in here so we can actually watch and look at what that algorithm does in real time and then change the algorithm to match what we want from gameplay perspective. Anyways, this has been another one of those visualization show-offs, and I'll be back with hopefully another video that's actually more gameplay related